So let me begin by thanking the organizers for inviting me for this. This is my fourth QMAT, and yeah, it's very exciting to be here. So today I'm going to talk about the emerging superconducting phases in some new systems which are p-wave magnets. This is mostly, I would say, that is a theoretical investigation for us, and I will show that by doing simple mean field theory, that what are the emerging phases in this unconventional magnets. And this work is being done with my student Amartya, who is a very bright student. Next month he is moving to Stuttgart for his postdoc. And Paramita, who is here. Basically, I must say that Paramita has done the guidance for this project. And this is the archive version. So again, I mean, this paper is under review in PRL, but we don't know. Let's see. Okay. So outline of the talk is that first I would like to give you an introduction to the p-wave magnets. So because nowadays we are going through different kind of magnets like ultramagnet, etc. So just a difference between them. Then I would tell you that what we have taken is a very simple model of this p-wave magnet that has been proposed before us by some other group, and then the results that. So from the mean field self-consistent mean field calculation, that what are the phenomena that one can realize in this kind of p-wave magnets. So basically, I will talk about that three phenomena, which is in the phase diagram, which is one of the topological superconductivity, then the emergence of Bogoliubov Fermi surface, and that is the exotic superconducting diode effect. From the same phase diagram, I will tell you that these three things will appear. But anyway, I mean, it's difficult to give the introduction of all these three things. So before describing each phenomena, I will give you a short definition of this thing. Then I will summarize. So let us start with because we know that in our quantum mechanics we learn different kind of orbitals like S wave, P wave, and D wave. For example, when you do hydrogen atom problem. So in superconductor also different depending on the pairing symmetry, and we can have different order like S wave or P wave or D wave. So similarly, in recent times, we have seen that the magnetism also have this similar kind of following this. So the different kind of orders. So like if I define that ferromagnet and antiferromagnet is like S wave, because the magnetic order is momentum independent. So then the D wave magnet, which is one of the prime research interest of the community, is the ultramagnet. So D wave ultramagnet is one of the caricature, but there are many other G, I, etc. also is possible. So here the thing is that it's a D wave, so it's an even parity magnetic order. So and the magnetic order is definitely momentum dependent, so it follows the even parity. But for the p-wave magnet, that was first proposed by this Liebersmichel and Gyro-Sinebas group in these two papers, where they proposed that there can be a system where you can have odd parity in the order. So our focus will be like to write a simple model for this kind of magnet and to see the effect superconductivity. So again, just to in this single slide, that if you have ferromagnet, then you have spin split band and your time reversal is broken, parity is preserved, and net magnetization is non-zero. And if you take antiferromagnet, then both the time reversal and parity is preserved. You don't have any spin split band because up and down polarized polarized bands are at the same energy, and net magnetization is 0. There is no spin split band. For altermagnet, for example, if you have the d wave altermagnet, you have you have a different symmetry, which is the rotational symmetry along with the parity. So you have again time reversal is broken, but parity is there, so PT symmetry is broken. You have spin split band. Yes, you have momentum dependent spin split band, but the net magnetization is again 0. And similarly, in the p wave magnet, you can see that your time reversal is preserved. What you break is the parity or the inversion symmetry. And again, your magnetic order or the Fermi surface for the up and down spin polarized bands, they are splitted. You have momentum dependent spin polarized band. And net magnetization is again 0. So here, okay. Yeah, so in this paper actually, so they propose when the Spickles group, so they propose that the p wave magnets are basically a class of non-collinear compensated magnetic order. It's a kind of special kind of non-collinear system. So you can see that this is kind of a unit cell here and of this system. So for them there is a candidate material of this, and here the magnetic order is look like this. So where the alpha is the strength of this magnetic order, and so net magnetization is 0, and the reason is that you have the here the spin rotation and the translational symmetry. So this is the protection you have in this. Even if it is a non-collinear compensated magnetic order, you have to satisfy this symmetry. And you can see that if you have a spin rotation, then they will go to up and they will go to down. And if you do half spin translational, then you can repeat the system. So their claim is that this order mimics like spin orbit coupling, because it breaks inversion, mimics spin orbit. So one don't have to rely on heavy elements. And so okay. So the definition for us is that this is a special kind of non-collinear compensated order. This p wave magnet, it satisfies special symmetry, and it also has spin dependent magnetic order, but time reversal symmetry is preserved. So later on, so Jacob-Linder's group actually they propose more simple model of this p wave magnet that I will tell you when I will describe our system. So what is the motivation that what we look forward is to see theoretically to see the interplay of magnetism and superconductivity. Okay, so the first question that we ask several questions, that because what can happen in this. So in this picture actually you have the answer or the questions is it possible to find topological superconductivity in this p wave magnets, because I don't need any spin orbit coupling or Zeeman field, which is the essential ingredient to have topological superconductivity in engineered system. Or can I have some ground state which is finite momentum like Fulde-Ferrel or Larkin-Ovchinnikov phase? So that if I have this kind of phase, then can this pairing, if I have this finite momentum phase, then can it generate the Bogoliubov Fermi surface? And not only that, can I have the superconducting diode effect? Okay, so now let us the model that is proposed here. So we took the model of this p wave magnet, where this model is more simplified, but you can see that again this model still holds the symmetry that I told you. So this is you need this p wave order which is along sigma z, but you need this exchange term, which is like exchange between the localized spin and the itinerant electrons. This exchange term is along the sigma x. So these two, interplay of these two creates the non-collinear texture of the p wave magnetism in this. And if you see more closely, this system satisfies the time reversal and half translational symmetry, or spin rotation half translational symmetry. And I need a magnet. So I have applied a magnetic field, but the need of the magnetic field is slightly different. So I will tell you that why I also need the magnetic field to see some of the phases that I am talking about, or some of the phenomena that I am talking about. So okay. So to start with, so question. So I have read out the question, but again for all of you, that can I have topological superconductivity, Bogoliubov Fermi surface, and superconducting diode under the same umbrella in this p wave magnet. Yeah, individually, I can see this individually these three things in other systems also. I mean, we have work on alter magnet where you can see topological superconductivity and SD, but not all the three of them. Yes. Yes.
Yeah. So can you please explain like what's the microscopic origin of this term?
So here the microscopic okay. So this Hamiltonian they have derived from some k dot p theory, from the k dot p theory, from the. So I can tell you later how to obtain this p wave order from the correlation, which we have not taken, but I can tell you personally how to do it. Yeah. So before going to the details, if I look at the band structure or the Fermi surface of the up and down spin, so you can see that when you have only the tight binding, this is the 2D tight binding Fermi surface. You add the p wave magnetic term, it's like a rush bite, up and down spin band gets separated, and now in presence of this exchange term. Basically, what happens is that you brings the degeneracy at k is equal to kx, ky, here. So this now it is an effective two helical band, and if we apply an external magnetic field, there you can see you start getting band asymmetry here. So this gap system will give you the hint to have topological superconductivity, but the presence of both magnetic field. So this will give you the hint of to get a gapless LO phase, but this and also this is a very important phase where you can have the band asymmetry and the finite momentum generation. That is important to have the superconducting diode. So I will tell you slightly more later. So okay, so this is the yeah. So this is our phase diagram. So what we have done, we have added the attractive electron-electron interaction, and we have done the self-consistent mean field theory in the BCS and the FFLO channel. And so the phase diagram is telling you that, so in one axis you have this exchange term with the JSD between the electrons and the itinerant electrons and the localized spin, and B is the external magnetic field. So here in this line, when this B is 0, you can see that there is a transition from the BCS to topological superconductor, so trivial to topological. And along this line, you have a transition from the BCS to a LO phase. So this is the gapless phase, LO phase. Now in presence of these two, you can have different phases, which is the gapped FF phase, the gapless FF. And when both the B and the JSD is large, you get your superconductivity is destroyed. It's a normal metal. And this is here we are plotting the other parameter, because due to finite FFLO generation, you have the finite momentum, and so this is in the FF phase you have the finite momentum and the LO phase also, and this is the free energy. It's showing you that you have the free energy minima in here. So here the free energy minima, but there is asymmetry along the x direction in the qx. but the QY is symmetric in the FF phase. But in the LO phase, actually what happens is this, your free energy is symmetric along both X and Y. Okay, so the first phase is that the topological superconductivity, which is along, so this is the along this line. So just to give you a picture that in 2D, so you can have different kind of, so if you have a, so it's shown before that in 2D topological superconductor, you can have different kind of boundary modes. So if it is a Px plus IPy order in the topological superconductor, then you can have a dispersive edge mode. But if you have a Px plus Py type pairing, then you can have a edge mode, but which is a flat edge mode. So just to differentiate between these two kind of Majorana edge mode, so what kind of edge mode we are getting here? We are getting actually the flat edge mode. The reason is that if you look at the bulk spectrum along in this phase, you can see this is a gapless. You have 4 gapless points here. It's like vortex, anti-vortex here. So this kind of gapless phase always gives rise to this flat edge mode. That is not new. It is known in the literature, and because as it is gapless, so there is a possibility to characterize this by this winding number, but as a function of ky, I don't have a 2D proper invariant to characterize this flat edge mode. And also in the eigenvalue spectrum, you can see that at the 0 energy, you have this flatness of this edge mode, and also as a function of the ky and this JSD parameter, you can see that these two is like this is the presence of the this flat edge mode in this parameter space, where the nx becomes 2. Yeah, here nx becomes 2 because this here you have actually 2 degenerate flat edge mode because of these 4 gapless points. Okay, so this is the first appearance of Majorana flat edge mode without rush bar spin orbit coupling and the magnetic field, because in this line magnetic field is 0. Although the topological phase slightly exists here also in this line, I mean in this small region, slightly infinitesimal magnetic field also survives this topological phase. Now, so one slide about the BFS. So what is the Bogoliubov Fermi surface? Is that in some gapless superconductor, what can happen is that you can some new Fermi surface can appear in some gapless superconductor. So the dimension of this Fermi surface will be equal to the dimension of the normal Fermi surface. For example, in 2 dimension, if you see the D-wave superconductor, so D-wave superconductor has these 2 nodal lines, and these 2 nodal lines cut the Fermi surface along these 4 points. But now if you apply some magnetic field, what happens is these points here, these cutting points here, these points start getting elevated, and these are the again these are 2D Fermi surface which has the same dimension of the, because these are 2D. So this, what is the kind of how to see that? I mean, if you look at the density of state of the superconductor, so you need a magnetic field to generate this in this gapless space. It's shown much before by the Hirschfeld group. So when B is 0, you have the usual superconductor, and this is as this are gapless superconductor. So you can see that B is equal to 0. You have this gapless points. So this is the density of state for B is equal to 0. Now if you apply magnetic field and start increasing the strength of the magnetic field, you have elevated density of states that is appearing at 0 energy. So this elevated density of states is kind of the signal of the appearance of the Bogoliubov Fermi surface. And similarly in Carsten Thiem's group, they have shown this generation of this Bogoliubov Fermi surface in 3-dimensional superconductor, or I mean in spin 3-half superconductor, where you can see, so you have this fat region is the appearance of BFs. So in our case, again, so if I look at these gapless phases, so we looked at the Fermi surface, so we can see that these are the emergence of the Fermi surface in this LO, gapless LO and the gapless FF phase. And if I look at the density of state in those regime, so for both the phases, you can see that there is an elevated increase of the density of state due to the generation of Bogoliubov Fermi surface. And if you look at the density of state at exactly at E is equal to 0 in the parameter space, so this is the non-zero density of state kind of characterizing the Bogoliubov Fermi surface, which is 0 in the gapped region and quite a large value in the maximum in the metallic regime. Okay, so how I am doing?
Yeah, 5 minutes.
5 minutes. Okay, good. So okay, so the third phenomena, which is the superconducting diode. So just to give one slide for you, what is the superconducting diode? If some of you has attended Sudeep's talks yesterday, he has defined it. So superconducting diode means you have to create some non-reciprocity in the supercurrent. So usually, if you break the time reversal and inversion, both the symmetries in a superconductor, then what can happen is that the forward moving supercurrent and the backward moving supercurrent, there can be a non-reciprocity. So this red line, and if you switch, just make the sign of this B and eta parameter opposite, so there is this non-reciprocity in the negative direction. But anyway, it's the same thing. So the thing is that the current before the superconductivity is destroyed, the supercurrent, the critical supercurrent for the forward and backward should be different. And to create this non-reciprocity, you have to break some symmetry. And in our system, the p-wave magnetic order breaks the inversion. And I have applied a magnetic field, so that breaks the time reversal. And why I need to break both the symmetries? Because if you look at the system only with Rajba spin orbit coupling, then you can see that your band has splitted, but your center of mass doesn't get any, you don't generate any finite center of mass momentum. Even with magnetic field, you can generate a finite mass momentum, but that is same. That is similar in the positive and in the negative direction. So the effective, the net momentum is still 0. But if you have both the spin orbit and the magnetic field, you can generate a finite momentum pairing, which is the Fulde-Ferrell-Larkin-Ovchinnikov that I am talking about so far. So so this situation cannot give you a diode current because still you don't get any net momentum. But here in this phase, you can actually generate a finite momentum, and this pairing generation is essential to have the diode effect. So now in this phase where I have this gapped FF, the Fulde-Ferrell phase where I have generated the finite momentum, and here you can see again I am showing you the free energy, where you can see that the free energy minima in the so you have generated the free energy minima in the QS direction, or the X direction is asymmetric, but the Y is still symmetric. So now if I plot the current, the Jx and Jy in this Qx, Qy plane, you can see that I have the asymmetry, non-reciprocity in the Jx, but I don't have any non-reciprocity in the Jy in this 2D system. And if I see the efficiency of this diode current as a function of this magnetic field, then you can see that as I increase the magnetic field, so this diode current increases because of the generation of this phase. For any JSD value, if I increase this magnetic field, I get the FF phase. But but then again, for high magnetic field, the current, the efficiency decreases because of the uh, I mean, the superconducting order gets smaller and smaller for a large magnetic field. And in this gapless region also, you will get some finite diode current, but that is smaller in magnitude, because in this gapless space, you also have the Bogoliubov Fermi surface, which is a mixture of both Cooper pair and quasi-particles. So due to the presence of quasi-particles in the PFS, actually diode current will decrease. And then again, this increment here, this small increment is kind of, the asymmetry is becoming very small, and also this numerator denominator both are becoming very small. So it can show some anomalous behavior, but actually this is not that important. Okay, so what is the take-home message? Is that so what I'm trying to convince you that in this p-wave magnet, actually in this special non-collinear textured magnet, within self-consistent mean field approach and taking up a simple k dot p derived model, I can have topological superconductivity, but this is a weak topological superconductivity because the bulk is gapless, and I have the flat edge mode. But I don't need any Rashba spin orbit and the external Zeeman field for that. My p-wave magnet itself can do that. And also, I can generate the Bogoliubov Fermi surface driven by finite momentum superconducting order in the gapless LO and gapless FF phase. And if I apply the magnetic field, I can, in the density of state, I can see that the enhancement, the density of state in presence of magnetic field, that is the kind of signal of this generation of BFS. And now I can have also the superconducting diode. I can generate non-reciprocity in the current through this system. And in this FF phase, I can have the superconducting diode. So that means this p-wave magnet can be a fertile platform for realizing different superconducting phenomena. But however, I mean, we don't know any materials which will mimic all this physics that I am going to talk about. And here I want to advertise this. So how to realize, this recent work of ours is how to generate a higher order topological superconducting phase in p-wave altermagnet heterostructure. So one of my postdoc Kaushik will give talk on this. If you are interested, you can attend. And also, this is a very recent work of ours, is that superconducting diode via Floquet-Majorana modes. So how the Floquet 0 or pi Majorana modes selectively can generate non-reciprocity internally and can give diode current in driven Rashba nanowire. That my student Shayuk will give a talk tomorrow. So if you are interested, you are welcome to attend. Okay, thank you.
Thank you very much. So floor is open for questions, comments.
So in that superconductor, there is no spin orbit to begin with.
No, look.
So you said it's without Rashba that.
You start from a p-wave magnet. Okay. P-wave magnet, and then it's a completely microscopic calculation because I add this attractive Coulomb interaction.
Right.
And
so the reason I'm asking is because this without Rashba having these flat band Majoranas can be done with these nodal superconductors as well, these Ising superconductors. So I'm just wondering if there could be some parallel.
As in my superconductor, you have this kind of Ising superconductor, Ising spin orbit is like a magnetic field.
Yeah. So I'm just wondering if some parallels can be drawn, because the main difference I can see from here to there.
Yes, you can, because I can tell you that look at the Hamiltonian. Yeah. So this is kind of Rashba.
Yes.
Yeah, but it is sigma z. Okay. And this is this JSD, which is the exchange term between the localized spin and the itinerant electrons. So these two.
Sigma z isn't it more like Ising than Rashba?
No, it's not Ising. Ising is just alpha sigma z. It doesn't have the momentum dependence. Okay.
One more question. Is there any? All right. I think if there's no more question, let's take the speaker.